Okay, so first of all, thanks for the great opportunity to speak here in front of such an experienced audience. Yeah, as said, this talk is about LibTrixi. And okay. Well, give me a second. Okay, why not? Okay, I'll do it like that. Okay, so LibTrixi is an interface library to the computational fluid dynamics solver Trixi.jl. And Trixi.jl is written in Julia. And the interface we now want to come up with is an interface from C, C++, or Fortran to Julia. And that might be the most unusual thing here. And we plan to use that for HPC simulations and Earth system modeling. Yeah, these guys are sitting over there on the other side of the floor, unfortunately. But yeah, nevertheless, these are our applications here. Yeah, and I will walk you through why we do need such an interface at all and how we did it and what we're currently doing with that. Okay, so why? Of course, there's a project. It's called AdaptX. That's an acronym. It has a really large title. And it's, of course, on Earth system modeling and making it exascale ready. And I could go into details here, but I won't. Instead, somebody else did that. So last month, I was at Zurich at the PASC conference. And there was a very interesting talk by Chris Maynard from the Met Office UK. Yeah, and he basically nailed it. So that's just a screenshot of his talk. That's not in my official slides. So he was talking about the old approach they had in their code, in their dynamical core, and what they're currently doing. And so he used, so he said, so there were these great old times where you had a high-level language like Fortran, which the domain scientists could use for writing up their mathematical model in a very concise, textual manner, which everyone could understand. And then you had a very powerful compiler, which would then transform that to machine-specific instructions, and you had performant code. And yeah, as he remarked, that's a nice separation of concerns for domain scientists on the one hand side and computer scientists on the other hand. And now you have all these other things. You have GPUs, memory, performance, all these things you have to care about, and that breaks essentially this separation of concerns. And of course, there are lots of tools to help you with that. But in the end, of course, still a domain scientist would need to know about all of this stuff. He would need to be educated in how to do it properly. And yeah, maybe that's not what he essentially wants to do. So that's a nice picture here. So his claim was things should be more simple again. And okay, there were lots of people at this conference from all these institutions doing climate and weather modelings. And what they usually have in mind is to come up with kind of a generator approach where you, for example, use Python to generate code in an intermediate language, and you then compile that code to efficient code. But yeah, thinking about that once again, so on the one hand side, a high-level language, and on the other hand side, efficient code, and that's Julia conference here, right? Okay, so why not do that in Julia? That's our idea. Yeah. We have Trixi on the one hand side, our main program on the other hand side, and we have our library in between, and that is composed of a Julia part, a C, and a Fortran part, and yeah, I will just quickly walk you through. But first things first, Trixi.jl, that's the flow solver that we are connecting here. It is a simulation framework for conservation laws. It's built around an adaptive, high-order, discontinuous lurking method. Let's say one of the outstanding features is the entropy stable and entropy conserving methods that it implements. And yeah, our community and also our features have grown considerably large during the last years. Yeah, here's a QR code if you're interested in that. And we also have a YouTube channel. And of course, okay, yeah, that was just to put the VLAN to a test, but also that works. Okay, great. Yeah, so that's, for example, that's a demo of the adaptive mesh refinement features you have in Trixi. All right. Okay, so now I'm lost in YouTube. Okay, so continuing with that. So now we are on the right-hand side still. So that's our interface, like on using Trixi.jl for an actual simulation. To set this up or to configure that, we have Trixi as a library, so we do the configuration through code. And the code is what we call an elixir. And it looks like that. So going up here. So you have, of course, to include Trixi and also now LibTrixi here. And then you can specify your equations, the solver, a mesh, initial conditions. And then you put this all together into an object that we call a semi-discretization because of the PDE we want to solve. And then you define the time span. And we have a routine that's called semi-discretize, which then transforms this to an ODE object, and that can be passed on to ordinary diffie-q. And then this does the integration in time. And now here for LibTrixi, we pack all these things together into an object that we call a simulation state, and that is something that we save. All right, that was the first part. Now we come to the interface. And here we have at first a Julia API. So a Julia API to Trixi.jl, which is also a Julia code. But the reason for doing that is that we have we need to somehow translate the complex data structures that we have in Trixi. And so the final goal is you have to kind of come up with an interface which has just these integral data types that you can then pass around when coding that from C. So it typically works like that. So for example, you want to get the number of elements. We have such routines here in Trixi, which then get these objects that we put all into the semi-discretization object. It kind of unpacks them, and then you can call these internal routines that are there in Trixi. And that's maybe the most interesting part here now. On the Julia side, we use this base C callable macro, and here below the add C function macro to get a function pointer to this routine that we just implemented in Julia. And what it does, it fetches this simulation state, and then it just calls the Julia function that we defined up there. Okay, so the next building block is then the C API. So we just have these, we just generated these Julia functions, which are C callable. And we now have to remember the name that we gave to these functions, so these C function calls. And now on the C side, we can now here use the Julia C API to just evaluate the string that I put here in the first line. And Julia will evaluate the string and will then return a function pointer to this internal routine. And it comes as a void pointer, and we store it on the C side. Later on, if you then actually want to call this function, you of course have to get this function pointer once again, and then you can really cast it to to your actual functional syntax, and then call the function. That's the C API. Our next part is Fortran, and that's rather simple because once you have a C library, calling that from Fortran is rather easy. You just have to write this interface around that. Okay. So of course that was tedious. So there were at least 4 points where you, 4 different files, maybe more if you include header files, where you have to kind of put these things together and remember all the names and have it done consistently. And but on the other side, it's really easy to do that. So I call it GenLibTrixi.jl working title maybe. So that's in the end a helper script which just takes such a YAML file where you specify how it should be called and what the docs are like and what the return type is like. And then it generates all this interface stuff with some gap texts where you have to-do markers. And that are the places where you actually have to do something, where you need to think about, like actually calling Trixi functions. Okay, so how to use this library in the end? It is a CMake project, so you can just configure and build it. And for writing your main project, so to say, you have to, in case of Fortran, include the model, of course, compile that, and link it to LibTrixi SO. And that, for example, in the most basic form could look like that. So you include LibTrixi. You have to initialize the Julia runtime environment. You have to initialize the Trixi simulation. And then the most simple main loop would be this, like, if it's not finished, then do another step. And then you have to finalize it at some point. And that's it. So it's an interface library. Of course, it's interesting if it impedes performance. And of course, it does not. So we have some very simple benchmark problems here, one in 2D and a moderately sized one in 3D, just implementing the compressible Euler equations. And yeah, for this small example, you can see that, of course, there's an overhead. But if you move to a, let's say, reasonably sized application, then it does not matter anymore. So that just tells us that LibTrixi is kind of as fast as LibTrixi.jl, which is just the Julia interface, which is nearly as fast as native Trixi.jl. And that's good because because we already know that the performance of Trixi.jl has been shown to be on par, or maybe even better at some points, than classical codes, so codes written in these classical HPC languages. Here's the reference. All right, just want to show some results. So our, let's say, most loyal customer, and also the only one, is Massey. And that's the Modular Earth Submodel System. That's one of the cooperation partners in this project I mentioned in the beginning. And that's a large framework which couples physical model, dynamical cores, all those things. And it's written in Fortran. So they actually want to use Trixi now as a kind of replacement of the current dynamical core, which is known to, for example, not scale very well and not be GPU compatible and things like that. Yeah, here is the baroclinic instability. This is kind of a standard test case in atmospheric flows, and you have seen the video on the first slide. Okay, so it's not a very large test case. It has very few cells, but as the polynomial degree is high, you get this large count of degrees of freedom here. And yeah, we can now, of course, run that on a supercomputer using LibTrixi. And these are experiments that we did at Jülich Supercomputing Center. And here you can really see that it scales very well. And that's, of course, not my achievement. It's the achievement of Trixi.jl, but we can now directly use that here. Yeah, and another thing I'm really happy about is that we now can also leverage GPU offloading capabilities. And that's really bleeding edge. So it was just last Tuesday when our student Lars announced that he finally did his first draft of a multi-GPU version of Trixi.jl. And that's based on CUDA-aware MPI, on kernel abstractions, and on adapt.jl. And what I did here is I just took the same example, this baroclinic instability that we have seen before, and used exactly this problem with the same size and ran it on 1 GPU, 2 GPUs, 4 GPUs. So not this massive GPU counts that we have seen before. And also, of course, I have to mention that the scaling is not ideal yet. And also the numbers on the y-axis here are not the same as before. So it does not compare well to the CPU implementation yet. But of course, as I said, that is work in progress, and Lars already figured out some places where our data structures kind of interfere with making this highly performant. Yeah, but the cool thing, and that's my main message here, is that it works. And if you think about this nice switch that we have seen on one of the first slide, so here's our code, this semi-discretization, and now we have this adapt to Q array keyword here. And if you do that, then GPU offloading is enabled. So GPU offloading on, off, things like that. I really like that. So what's the time?
5 minutes.
Okay, so can take some time to tell you about our next step. So what are the things that we are going to do next? First thing that's already there in Trixi is adaptive mesh refinement. And of course, we would like to use this here. So this is the first try to run that for the baroclinic instability. So when the instability comes up here, you see that we get refined elements here. Unfortunately, so this is actually a 3D test case. So it discretizes the whole atmosphere. And if you get these non-conforming interfaces in the vertical directions, then our DG scheme sometimes develops some instabilities with this. You have hydrostatic balance profile there, and that seems to cause some issues. And of course, we will now look into this because we are really convinced that AMR would be nice to have. And as said before, we of course would like to improve the multi-GPU performance. And then we will look into more advanced models for atmospheric flows, because right now for messy sites, that's kind of a toy problem. They just started and are happy with the results. But of course, we would like to get some real mutual coupling. So integrating their physical models and our flow solver. And in order to do so, we have to extend Trixi a little bit. And we also have a sub-project for that now. It's called Trixi Atmo, and that has also been just started. Yeah, that was another point. Also in my abstract, I announced that we did some experiments with a package compiler, and we did that, and it worked. But our executables were quite large. But we had this nice talk here on new ways to compile Julia code, and there was also Julia C mentioned, and that seems really attractive to us because so we have Messi as our main customer, and they are non-Julians. So when we tell them about that they have to set up this Julia runtime environment, and sometimes it might fail due to some reasons, that might scare them off. So if we can at some point tell them, okay, there's just one shared object, you have to link it, and you do not need to care about anything else, they will probably be happy. And some final thinking here. So for these atmospheric simulations, single precision should in principle be enough. And we are currently working on that. So I'm not working on that, but fortunately we have other people working on that. That will make it possible to do the whole simulation in single precision. And that will allow us to use like prosumer GPUs, because we, at least in our institute, do not have these data center GPUs available. All right, yeah, final slide. Thanks a lot to Julia community. So I just started that last year, and so far it has been a real pleasant journey. And as I told you, we are using lots of these incredible packages. Thanks to the Trixi community. Also, as I told you, that most of the things are not my achievement. It had already been there. I just had to be adopted in this interface. Thanks to Michael, who had come up with this idea for LibTrixi. So when I started, basically, he had already figured out all the technical details for that. Yeah, thanks to Lars for his multi-GPU implementations, which he finished last Tuesday. And to JuliaCon Computing Center for the resources. We have a reproducibility repository. It's at this URL, and in the QR code below, the QR code on top is for LibTrixi itself. Yeah, thanks for your attention.
Thank you very much. Are there any questions? So I think Boris was first.
Do you have an issue with the garbage collector interfering when you call Julia many times from C?
As far as I can tell so far, we did not have any issues.
Okay, and yeah.
If it's successful with the Messi collaborator, would that be the majority of the compute, or do they have lots of back-end algorithms?
That's a good question. So when we had our discussions with them, they would usually tell us that they have chemistry, some chemistry going on. And that also seems to be a large fraction of the computational time. But yeah, the motivation for this project was that the dynamical core that they currently use, which implements a spectral element method, that this is not capable of running on current supercomputers, and especially not on the upcoming generation.
Okay, it's even better, like it's too big to even work.
Yeah.
Okay, great.
Are there any other questions? Yeah.
Thanks for the talk. How would you manage the dynamic load balancing from the C side? Is this something that Trixi does, so you can just profit from it in these future steps that you were mentioning?
Exactly, yeah.
Okay.
That's all supplied by Trixi. Yeah. It has this meshing backend P-forest or TAT code in the future, and that does all the balancing. Yeah.
Okay, thanks.
Then one last question, and the next speaker can already set up everything.
I have a question about the least CPU-intensive part of the process, generating the wrappers. I liked what you did with the YAML file. Do you think that, I mean, it looked as if that would probably even be quite generalizable, because writing boilerplate code is never fun.
Yes.
So anything that we can make a bit easier would be dead useful.
I'm sorry, and your question was about the speed
Well,
of that?
is it, you know, this GenLibTrixi, if I remember the name
It's just
correctly.
a working title. I mean, it's just
Yeah,
a script
but-
that I have on my laptop.
But it was just, it just struck me that I mean, it's a simple thing, but it's also quite an annoying thing to get wrong. It would be quite nice if that was, you know, just like generate C Fortran wrappers, and
Okay.
it could work for anything and for anybody.
Yeah, thanks for the comment. Yeah, and that's not yet done. So it's very specific for my personal use case. But yeah, of course. In 90% of all the cases, it just works, and the other 10%, I would have to figure out. Yeah.
Oh, great. Thank you for the talk again.